One interesting effect is the Doppler effect. We are all familiar with this effect. If you are standing on the side of the street, if a car or a truck is moving while its horn is blowing, the frequency of the sound you hear is higher as the vehicle approaches you and lower as it moves away from you. This is Doppler effect. As you can see in this illustration, because of motion, there will be an additional wave front detected, which is distance divided by lambda of the source. Distance is v naught t, velocity multiplied by time. And this will result in a change in the frequency. So the observed frequency is equal to the source frequency plus the new value v naught over lambda s. Lambda s, the wavelength of the source, can be calculated. The velocity divided by the frequency, as always. So the frequency heard by the observer can be calculated from this equation, v plus v naught divided by v. If the observer is moving away from the source, the frequency now becomes less than the source frequency. So the observer frequency is the source frequency multiplied by v minus v naught divided by v. V naught is the speed of the observer and v is the speed of sound. We are assuming the source at rest. If the source is moving, then we need to take the velocity of the source into consideration. So here, if the observer is at rest and the source is moving, the observed frequency can be calculated from this equation. If the source is approaching the observer frequency will be higher, the pitch of the sound will be higher, and calculated from this equation, v divided by v minus vs. V is the speed of sound and vs is the velocity of the source. In general, we may use this equation for various scenarios, for various cases. The observed frequency is equal to the source frequency multiplied by v plus v naught divided by v minus vs. V is the speed of sound, VO is the velocity of the observer, Vs is the velocity of the source. If the observer is not moving, just substitute 0. If the source is not moving, just substitute 0. Then, if they are moving toward each other, you need to have observed frequency greater than the source frequency. So this would be plus, it would be minus. If they are moving away from each other, you substitute here negative value. So this becomes a plus, and negative value, this becomes minus. So the observed frequency becomes less than the source frequency. Suppose you are on a hot air balloon ride carrying a buzzer that emits a sound of frequency F. If you accidentally drop the buzzer over the side while the balloon is rising at constant speed, what can you conclude about the sound you hear as the buzzer falls toward the ground? So in this example, the source of sound is moving away. The source of sound is moving away. Therefore, the frequency that you hear as an observer should decrease, and also the intensity should decrease. The intensity depends on r, the distance, r squared. Okay, so it will decrease according to an inverse square law. and the frequency will decrease according to the formula that we have here for the Doppler effect. Another phenomena associated with the motion of the source is the shock waves. If the source is moving and accelerating at one point, its velocity may exceed the velocity of sound. Under such conditions, a shock wave will be created, as you can see here. A shock wave will be created, and then after the shock wave, the source will be faster than sound in air. Usually, when we describe such a situation, we use the Mach number. We divide the Mach number as the ratio between the source speed and the speed of sound, Vs divided by V. So if the source speed is equal to the speed of sound, this corresponds to 1 Mach. It is common in jet fighters to have jet fighters with 2 Mach or even higher velocities. So shock waves happen when the source speed exceeds the velocity of sound. When this exceeds 1, then you will have a shock wave. This is another example of the V-shaped shock waves produced by a boat when the boat speed exceeds the speed of the water waves. So here we have speed of water waves compared to the speed of motion of the boat. It's very much similar to the situation for a plane in air. A boat in water is similar to a plane in air. Both can create a shock wave. The large pressure variation in the shock waves condenses water vapor into droplets. So when the jet fighter speed exceeds that of sound, we will see such a condensation for water vapor in the air. Simply as the plane is accelerating to higher and higher velocities, the pressure on the air molecules gets higher and higher until it penetrates this wave front when the velocity exceeds the speed of sound. As an airplane flying with constant velocity moves from a cold air mass into a warm air mass, the Mach number, remember, is the ratio between the speed of the source and the speed of sound. So the Mach number will decrease because the speed of sound increases in the warm air while the speed of the source, the plane, remains the same. Okay, so the Mach number decreases. Another phenomena of interest is interference. Sound waves may interfere with each other, and interference may result in constructive or destructive patterns, depending on the phase difference between the sources. If the path difference between the two sources is integer multiple wavelength, we have constructive interference, louder sounds. If the path difference R2 minus R1, this is the path difference. If it is integer multiple of lambda plus 1/2 wavelength, we have destructive interference, which will be reduced loudness or zero loudness.